Welcome back to the Trending Tech Show, where we break down the systems behind the services you rely on every day. Picture this. You're posting a photo online, and immediately your friend on another continent sees it. How does that happen so fast and reliably? Today, we're diving deep into a technology that makes this magic possible: database replication. Our goal is to pull back the curtain on how modern digital systems stay fast, reliable, and available, even when things go wrong. To guide us through the world of data replication, I'm joined by database expert Mike. Mike, thanks for coming on.
Hey Alex, thanks for having me. I'm excited to unpack data replication. It's one of those foundational building blocks that most people benefit from every day, but rarely think about.
Let's start at the very beginning. When we say replication in the context of databases, what exactly do we mean, and why is it so important?
Replication simply means maintaining copies of the same data on multiple machines, connected over a network. But the why is where it gets interesting. First, replication lets you keep data close to your users. So if someone in London and someone in Tokyo need the same info, you have copies in both places, reducing delay or latency. Second, it's an essential ingredient for keeping systems robust. If part of your system fails or goes offline, another copy can take over, so the service continues without a hiccup. And third, it's about scalability. By spreading read requests across several machines, you can handle many more users than you could with just one database.
So it's like making backup copies, but also about speed and making sure everyone can access stuff easily.
Exactly. But unlike backup copies, which you might only use in an emergency, replication is active. These machines are all working together in real time to keep data consistent and accessible. It's a backbone for high availability and performance.
I love that. Now, you mentioned keeping those copies consistent. Let's talk about the main approaches to replication. What are the basic models, and how do they work?
The three main replication models you'll see in practice are single leader, sometimes called master-slave, multi-leader, master-master, and leaderless, dynamo-style replication. Each model handles the challenge of distributing and updating those copies a bit differently. In single leader replication, one replica is the boss, the leader. All write operations go through this leader, and it sends changes to all the other replicas, which are called followers. The followers can handle read requests, but if you want to update data, it has to go through the leader. Multi-leader replication allows more than one node to accept writes. Each leader shares its changes with the other leaders, so the work gets distributed. Leaderless replication takes a whole different approach. Clients can write to any replica, and the system coordinates syncing and consistency across all the copies.
Let's take these one at a time. Single leader replication seems pretty straightforward. What does the process look like in action?
Imagine an online retailer. Orders and stock updates all go to one main database server, the leader. When it records a new purchase, it logs that change and pushes it out to its followers. The followers are up to date most of the time and can handle all those customers checking product details or browsing, but orders always go through the leader.
And if the leader fails for some reason, what happens?
Good question. If the leader fails, you need to designate a new leader, a process called failover. One of the followers gets promoted. Sometimes this process is automated, sometimes it's manual, but there's always some coordination involved. Picking the most up-to-date follower as the new leader helps reduce data loss, but if there's a lag, some very recent writes might not have made it to the others. That's a big trade-off in this architecture.
Does replication always happen at the same time as a write, or can it be delayed for performance?
This is where we get to one of the big configuration choices: synchronous versus asynchronous replication. In synchronous replication, the leader waits for at least one follower to confirm it received the change before telling the user the update is done. This way, if the leader suddenly fails, you know the data is still safe. The downside? It slows things down. If your network hiccups or a follower is slow, the whole system waits. Most real-world systems use a mix. Maybe one synchronous follower for safety, but the others are asynchronous, meaning the leader doesn't wait for confirmation before moving on. This keeps things fast, but comes with the risk that the very latest data might not be copied everywhere if the leader crashes unexpectedly.
That sounds like a tough decision. Can you give us some examples of where you'd want one over the other?
For banking or financial transactions, where losing even a single confirmed operation is unacceptable, you go with synchronous replication even if it's slower. But if you run a social media site where speed is king, and it's okay if, say, a like or a comment might briefly be missing after a crash, asynchronous replication gives you better performance.
Are there any major trade-offs or risks with asynchronous replication?
The biggest risk by far is data loss after a sudden leader failure. If the leader accepted a write, told the user it was successful, but hadn't yet sent it to the followers, that change could vanish if the leader dies at that moment. Also, asynchronous followers can fall behind if they've got a lot of catching up to do, maybe after being offline for a bit, leading to something called replication lag.
You just mentioned replication lag. Can you explain what that is and why it matters?
Absolutely. Replication lag is the time delay between when data is written to the leader and when it appears on the followers. Think of it like waiting for a message to reach all your friends in a group chat. Sometimes one person's phone is on airplane mode, so they see it late. Now, if a user writes data and then immediately tries to view it from a follower, they might not see their own update. This can be confusing or alarming. Lag becomes a critical issue in applications where immediate feedback matters, like user profile updates, financial transactions, or collaborative tools. It can also mess with consistency. If different users are reading from different replicas, they might see different versions of reality.
And are there strategies to reduce or mitigate replication lag?
There are. First, keeping your hardware and network healthy and not overloaded reduces lag. But also, some applications apply smart strategies, always reading from the leader for recently updated info, or only allowing users to see their own updates via the leader. There are also architectural techniques like prioritizing certain types of writes or using logical logs to catch followers up quickly. Monitoring is absolutely key. Most modern systems track lag and can alert you if it gets too high, so you can intervene before it impacts users.
Got it. What happens when the lag leads to those weird consistency problems? How can systems promise users they'll see their own changes?
You're hitting a big part of distributed database design: consistency models. With asynchronous replication, several types of consistency guarantees exist. One is read your writes consistency. That means, for at least a while after a user makes a change, all their reads go to the leader to be sure they see what they just did. Another is monotonic reads, which means if you see something new, the system shouldn't ever show you an older version again, even if you switch replicas. Some systems track the replication lag and won't serve reads from a lagging follower. Others may route all reads from the same user to the same replica, boosting the chance that you'll see an up-to-date view. But it's a balancing act. More consistency usually comes at the cost of performance or complexity.
Changing gears a bit. What if we want to allow more than one server to accept writes? That sounds simultaneously powerful and scary.
That's the multi-leader or master-master approach. Here, more than one node can accept and process updates. These changes get replicated to all other leader nodes. It's particularly useful when you have users spread out geographically. You can have a leader in each data center. So, users in London write to the London leader, users in Tokyo write to their local leader. This gives low write latency and keeps things running if one area loses connection to the others. But here comes the complexity. If the same piece of data gets updated in two places at once, you end up with a conflict.
What does a conflict look like in this context?
Imagine you and I both edit a shared document at the same time, but from different cities. Your change says the title should be hello, mine says hi. When those changes meet as the replicas sync up, the system has to decide which title should it keep, or should it try to merge them somehow. That's a write conflict. Some systems pick the latest change, last write wins, often using a timestamp. But this approach can lose data, and it may not fit every application. Others let you define custom conflict resolution logic, maybe merging changes if both are valid, or prompting a user to choose. There are also automated approaches, using data structures called CRDTs that can automatically merge changes for certain types of data, like shopping carts or lists.
CRDTs, as in conflict-free replicated data types.
That's right. These are clever data structures that ensure, no matter the order in which updates arrive, all replicas end up in the same state without manual intervention. They're not a fit for every data model, but they're powerful for things like collaborative editing or distributed counters.
All this sounds incredibly complex to get right. Is that why many systems don't use multi-leader replication everywhere?
The ability to accept writes in multiple places is great for resilience and low latency, but the complexity in managing conflicts and ensuring consistency is significant. It's typically used in special scenarios, like multi-data center setups, collaborative tools, or services that have to stay functional even if parts of the system are cut off due to network issues.
Next up is leaderless, or dynamo-style replication. Now that sounds like outright anarchy. How does that work?
Leaderless replication is actually very methodical. Any replica can accept reads or writes, which are then distributed across all replicas. To ensure data isn't lost and to maintain consistency, these systems use quorum mechanisms. Without a leader, you need rules to say how many replicas must agree to a write, the right quorum, and how many you must read from to ensure you have the latest data, the read quorum. By carefully tuning those numbers, you get flexibility. If the system's too busy or a replica's down, you can tolerate it and keep going.
Can you walk us through a real-world example of this?
It's a simple scenario. You have 3 replicas. For a write to succeed, at least 2 replicas must acknowledge it. Write quorum of 2. For a read, you ask 2 out of the 3 replicas for the data, read quorum of 2. As long as the total number of nodes responding to your read and write requests is more than the number of replicas, you can guarantee that you're getting the latest data, or at least that your read and write sets overlap. But sometimes, especially if there are network issues or nodes go down, writes and reads can succeed with fewer replicas. That's called a sloppy quorum. It's more about durability than consistency at that point. You can write anywhere, and the system will shuffle the data around later to bring everything up to speed.
What happens if changes come in at the same time? Say, 2 different values to the same record. How do leaderless systems resolve that?
This is where version vectors or vector clocks come in. Each write carries metadata about which versions it knows about. So when 2 versions arrive at different replicas, the system knows whether one supersedes the other or if they're truly concurrent. If they're concurrent, well, the client may get back both versions as siblings, and the application may need to merge them, either by combining them in some sensible way or picking a winner. Some databases, like Riak, use CRDTs here as well.
It's a bit like 2 people editing a shopping list at the same time. When you compare notes, you might add both changes to the final version, right?
Exactly. The system's job isn't necessarily to pick a winner, but to give you enough context so you never lose data. Then either the application or an automated rule merges the siblings into a final consistent state.
So given all these complexities, how do you choose between single leader, multi-leader, or leaderless replication for a real system?
It comes down to your application's needs. If you need strong consistency and can handle a single write source, single leader is simple and robust. If you need to accept writes from multiple sites, for example, to support offline edits or global collaboration, multi-leader might fit, but be ready to wrestle with conflict resolution. If your primary need is high availability, low latency, and you can live with eventual consistency, or if your application logic can efficiently merge updates, then leaderless replication can be a game changer. The tricky bit is, with more flexibility and availability, you typically give up on simplicity and sometimes on strict consistency. There are plenty of edge cases and failure modes to think through. Lag-induced anomalies, network partitions creating split-brain scenarios with multiple leaders thinking they're in charge, and subtle consistency bugs.
You mentioned split brain, which sounds terrifying. What is that? And how do systems guard against it?
Split brain occurs when, due to a network partition, 2 nodes both believe they're the current leader and both accept writes independently. When the partition heals, you risk having diverged data states. Reconciliation gets messy. Good systems employ fencing, consensus algorithms, or strict leader election logic to avoid or quickly resolve split-brain scenarios. For leaderless systems, quorum mechanisms and version vectors help, but operational vigilance is always required.
As we wrap up, what best practices or advice would you give to someone architecting a replicated database today?
Start by clarifying what matters most in your application: consistency, availability, latency, or resilience. Monitor your replication lag and consistency, and don't just assume your replicas are in sync, they often aren't. Choose the simplest replication model that meets your needs and thoroughly test failure and recovery scenarios. Implement robust monitoring and alerts to catch issues before they snowball. Finally, document and automate your failover and conflict resolution strategies, so when chaos inevitably strikes, you're ready.
Mike, this has been a fascinating and insightful conversation. Before we wrap up, let's summarize the main takeaways for our listeners. Replication is about keeping data copies on multiple machines to improve speed, reliability, and scale. The three main models, single leader, multi-leader, and leaderless, each offer unique trade-offs in complexity, consistency, and fault tolerance. Synchronous and asynchronous replication give you a lever between strong consistency and higher throughput, but introduce their own risks. Replication lag can cause real-world problems like stale reads or weird anomalies, so always be aware and design with these in mind. Conflict detection and resolution become critical in more flexible replication models. Tools like CRDTs, version vectors, and customized resolution logic can help. Operational best practices and robust monitoring are non-negotiable for keeping your replicated systems healthy. Mike, thanks so much for demystifying the challenges and magic of data replication.
Thanks, Alex. Always a pleasure. Replication is an art and a science, and ultimately, it's what lets us build the always-on, global digital experiences we all depend on.
And for our listeners, if you want to learn more or revisit any part of today's episode, be sure to check out the show notes. Don't forget to subscribe for more deep dives into the technologies shaping our future. Thanks for tuning in to the Trending Tech Show.